How's everyone this morning? All right, come on in and we'll start our Bible class. Okay. Welcome to Lakeside. If you're visiting this morning, we're happy that you're here. Thank you for showing up this morning, and we're going to be spending one more week on this part of the Bible study, and then we're going to move to microbiology. I know, some of you are excited. So, last week we talked about, what did we talk about last week? Someone help me out. Same thing we talked about the week before? Actually, it was not the same thing we talked about the week before, because I took a week off. Temperature.
We went through the list of things that had to be exact as far as the composition of that particular planet, or could not support life.
Yes, exactly. We talked through all the things that you have to get in order for a planet to be able to support life. And we looked at just the astounding list of conditions that you have to get. And at the end of it, we talked about something that, if you go through all of those things, your chance of getting a single planet is less than one. If you had 400 billion planets in our galaxy to choose from, the chance of one of them working out is not likely at that point, because just there's so many initial conditions, there's so many pieces that have to fall into place that we don't expect one planet to be able to survive all of that. And then we talked about how, well, you'll often hear this when you're talking to someone about astrophysics. They'll say, well, if you get enough planets in enough places, eventually one of them has to work out, which the chances of that happening is so small, it's functionally equivalent to zero. We talked about how if I gave you a trillionth of a penny, it doesn't help you go and buy your latte that morning at Starbucks. The cash register lady is going to just look at you and be like, you still owe me $3 for the latte. It still doesn't get you there. Yes?
It's interesting when we think about the people that lived in overseas were from us.
Mm-hmm.
The United States hadn't been explored or anything of that nature, and so when they leave across, they're taking the chance to find out what's going on, and it kind of makes me think about what we're looking at here too. We there's so much out there; it's just hard to tell what's going to come up on the radar.
Yeah, there's so much out there. They're like, well, so you mentioned people traveling overseas for a trip. Imagine that you had to sail across the sea, and I told you your chances of making it to the other side were 1 in whatever it was, hundreds of trillions to 0. Your chance of making it to the other side is functionally equivalent to 0. Like when you take that leap of faith and you get on that boat, you're basically signing up to die if that's the chance that you're thinking about. And if you want to think about that from a philosophical point, like think about at the end of this life, there is a real journey that's going to take place, and you have to be on one side or the other. And if you're on the wrong side, your chance of making it to the other side is functionally equivalent to 0. You shouldn't put your faith in those things. All right. This morning, we are talking about fine-tuning of all of the universe. So last week, and the 2 weeks before that, we were talking about the fine-tuning of the stars and the planets. This week, we're talking about the fine-tuning of the whole system itself. And I put a little thing on there. Has a super intellect monkeyed with the physics. Okay? So it's part of it's astrophysics, part of it is just regular physics, but we're looking at all the things that have to go right just in the universe at large. We're not just looking like, is the planet the right distance away? Is the star the right type? All of those things. We're looking at like the glue that holds the whole thing together, okay? So in nature, there's a whole bunch of things out there. These are all the physical constants. This is really hard to read. That helps you a little bit. I don't know what most of these are. I only know a couple of them. But all of these things, if you go out and you Google Wikipedia and you look at constants in nature, these are all of the basic facts that our world is built upon that have to have certain values, and we have to ask nature for what they are, okay? So like, none of these things can be derived from math equations. All of these things have to be measured somewhere inside of nature itself. So one of these, this is a very abbreviated list. There's like 60 of these things. So like, some of these are like the weight of a proton, or the mass and charge of an electron. Some of these are the gravitational constants. Some of these are the speed of light. Whatever they are, you have to find them in nature. You have to go out, you have to devise a test to measure them, and you have to ask nature, essentially, what's the value for this thing? All of the equations in physics rely on these things exclusively. So if you look at the equation for gravity, it's the gravitational constant, that first one up there, with the mass of those two bodies that you're looking at, with the distance that they are apart. If you know how heavy those objects are, and you know the distance that they are apart, but you don't know the gravitational constant in there, your physics equation doesn't help you a bit. It's absolutely worthless to you. So you have to know what is the force that is pulling those two things together in relations to its mass and its distance apart, okay? So, this is the very first time it was done. This is called the Cavendish Experiment. Henry Cavendish did this in 1798. He was trying to weigh the Earth, which is an incredible feat, thinking that you're standing on top of it. How do you weigh something if you're, that's as big as a planet? But he had thought that he could figure it out based on the Newton equations. So what he did is, in his shed in his backyard, he made this contraption, okay? He got two giant lead balls, okay, which are the purple ones on this side, and then he got two smaller lead balls, and he put them on this horizontal steel ball, steel rod, okay? And then what you do is, if you know the force that it takes to twist up a rope, you can put that whole thing on a rope, and you can measure how much those two balls want to get, the two smaller ones want to get pulled to the larger ones, and you can measure that in the twist of the rope, and that will tell you the gravitational forces between those two objects. So his estimate back in 1798 is only 1% off of the 2014 estimate for this equation, which is just astounding that he was able to do something like that. Some people credit him with creating the first measurement of gravitational constant. Some of them don't. It's kind of, he called it weighing the Earth, whereas some of the other physics people want to say, no, he was actually doing something else. But in general, he's the first one who's credited with figuring out one of these constants of nature. Okay, so move forward a little bit. It's now the 1950s. Fred Hoyle is working in his physics lab, and he's investigating how carbon is forming inside of stars. So we talked about last week or 2 weeks ago how the heavier elements essentially get cooked inside of a star through the fusion process. And he was working on looking at how carbon was formed, because everything in life is carbon-based. Sometimes you'll hear scientists out there saying like some life could be silicon based. It's not true. Like it just doesn't work that way. Everything in life has carbon atoms in it if it's alive, okay? So he was looking at all of the things and how you could get carbon fusion inside of a star, okay? The issue is what's called the 5-nucleon crevasse, okay? So if you got hydrogen, hydrogen will fuse and it will make helium, okay? And if you get helium, it will fuse and it will make something that has a 4-nucleon structure, okay? But there's nothing in there that's in a 5-nucleon structure. So what they thought was happening is that you would have fusion and it would slowly add one atom at a time to the nucleon of this thing and it would get bigger. The problem is when you get to the 5-nucleon structure, it decays almost instantaneously. So as soon as something fuses into it, it radioactive decays and it splits back into whatever it was going to form into. And so he was working through this and he actually found a way that it would work. It works with beryllium and helium fusion. The problem is that in order to get beryllium, which is its atomic structure is 8, and helium to fuse, that it only happens inside a very, very tightly controlled, very small range inside of a star. You have to have a lot of things going right in order for it to fuse carbon inside of a star, okay? So, imagine this. When he was looking at the amount of things that had to go right, he was shocked at how many precise things had to happen inside of a star in order for it to fuse carbon. Imagine this. Imagine you wake up on a spaceship and the spaceship is controlling the entire universe. And you look and you see a whole wall of dials out there, okay? And all of these dials have incredible amounts of precision to the end of them. It's not, so think of it like, think of it like, those old-time radios, the AM, FM radios, you had to turn the knob, okay? And if you turn the knob just a little too far one way, your radio station goes out of focus, right? Lots of you guys are used to it. All the young kids are like, what in the world is that? Like, you just push the button and it goes right where you want it to go. But in those old-timey radios, if you twisted the frequency just a smidgen off, your radio station came out of focus, okay? So imagine all the knobs are like that, but instead of like, you can twist it and you only have to get to, if your radio station's 107.1, you go to 107.1. But if imagine it's 107.0000000, and then it's a 1, and if you don't twist the knob just a smidgen right, it doesn't work, okay? So you're on this spaceship and you see all of these things, okay? And all of them have that level of precision. You're looking at one of them and it's labeled the gravitational constant, how precise gravity has to be. And you see all of these zeros out to the end of it, and you see one knob that's just barely tweaked to where it's supposed to be. And you see the mass of protons and electrons out there, and they are tweaked to exactly where they need to be. And then you look in, it shows you like the strong nuclear force, okay? This is the thing that holds all the atoms together inside of a nucleus, okay? That is exactly where it needs to be. And then you look at the decay rate between when an atom decays from one to another. That is exactly where it needs to be. And all in all. And you would think, well, someone messed with this spaceship. Someone put all of these things exactly where they're supposed to be. Nobody would wake up on the spaceship and think, you know what, I bet these are all just randomly out there. I bet I could tweak with them, and I bet it would be okay. So this is what we're looking at. These are the glue in the physics equations that hold everything together, okay? So we talked about strong nuclear force. That's the thing that holds all the protons and neutrons together inside of an atom, okay? The weak nuclear force is how atoms decay. It's the rate at which they decay, okay? Gravity You know that one. Electromagnetism, you know that one. Okay? And then we're going to look at the ratio of all these forces to each other. All right. If you're on the spaceship and you decide to tweak gravity, okay? Let's say you go up to the knob and against your better judgment, you just take the very last one at the end and you just twist it just a smidgen, okay? If you make gravity slightly weaker, then inside of a star, the temperature won't get hot enough to fuse all of these things together, okay? So if it doesn't get hot enough for the fusion, then it won't get hot enough to make all of the heavier elements that you're going to need, okay? So the beryllium and the helium don't fuse together to make carbon anymore. And if you don't have carbon, life terminates inside of your universe, okay? Let's say you go the other way. You make it just slightly stronger, okay? If you make it slightly stronger, the stars get too hot and they burn through all of the material that's inside of themselves too quickly, okay? And in addition to that, now your universe collapses back on itself. Like right now it's expanding, you tweak it just slightly stronger and it collapses amongst itself, okay? How much do you have to change it for it to matter? You would have to change it only 1 part in 10 to the 36th power, okay? That doesn't mean anything to anybody. Like, if I tell you you have to change it, it's fine-tuned to 1 part in the 36th power, that is a 1 or a decimal point followed by 36 zeros and then a number, okay? That's how precise is it. We have 36 dials in a row, and then the last one out there at the end is changed. Your chance of winning the lottery is 1 part in 10 to the 7th. It's easier to win the lottery 4 times in a row than it is to precisely place the value of gravity out there. If you look at the estimated number of seconds since time began, that is 1 part in 10 to the 20th power. The seconds since time began as estimated by 13.6 billion years ago. Okay? This is how precise gravity is designed inside our universe. If you take a tape measure and you stretch it from one side of the universe to the other side of the universe, and you take the tape measure and you put it in inch markers out there, gravity exists inside 1 inch of that tape measure stretched from one side of the universe to the other. And what we're talking about is we're talking about taking the value of gravity and we're going to move it 1 inch across the universe, either weaker or stronger. That is how precise gravity has been estimated to have been and how quickly life shrinks to zero if you start messing with it. Okay? That's just fascinating to me. A tape measure across the universe is just amazing. Okay. Well, let's not mess with gravity. That one's things go badly if we do that. Let's look at strong nuclear force, okay? This is the strongest of all of those 4 fundamental physics things that we're talking about, okay? If you change it and you make it slightly more powerful, okay? So slightly more powerful, everything wants to fuse together much more quickly, okay? If you do that, there's no hydrogen left inside the entire universe. So in our normal discussions of the universe, everything starts out at hydrogen, everything starts out at the lightest element, and then it eventually gets fused together, okay? If you make it where they want to fuse together a whole lot quicker, then you run out of the basic element of hydrogen pretty quickly, okay? If you make it slightly weaker, then they don't want to form together inside of a nucleus to begin with, okay? And then you end up with only hydrogen at the other end. So if you make it slightly stronger, everything wants to combine into heavier elements too quickly. If you make it slightly weaker, nothing wants to form into heavy elements, and all you get is the gas. Either way, you end up with a life-prohibiting universe. The estimated value that it has to be within 20% of its current value to permit life to exist. But another scientist had estimated it had to be within 0.5 to 4% of its current level to permit carbon production. All right. Oops. Okay. Electromagnetic force. Okay. So this is the stuff that lets all of our speakers work. This is the stuff that lets all of our, all our magnets, all our power generation work. If you change this and you make the electromagnetic force slightly stronger, okay? So now we're not looking at the center of the atom. We're looking at the electrons that are flying around this thing, okay? And we're going to change this. We're going to make this one slightly weaker. Then fusion becomes much less common, and you don't get these complex molecules to form. So anytime you're messing with this subatomic structure, anytime you're messing with the atoms and all of the stuff that messes with them, then you get all of these catastrophic reactions to occur. Yes, ma'am.
I was going to mention the last two things you're going over, the strong nuclear force and gravity. It's actually funny. Nowadays, so we kind of have a explanation as to how certain particles react and why. It's because of what's called the God particle. It's a Higgs boson. And there's a field called a Higgs field. But in quantum mechanics, you have like that tape measure theory. You have one particle, one end of the universe, and another one that's tied. So they're eternally tied together. And they have to react together in the same precision as they need to. And so it's like, think of it like married couples. You have a spouse here in Florida, Miami, Florida.
Okay.
You have the other one in Alaska, Anchorage. And then another couple, you have one in Maine. You have another one in Texas. It's kind of like that, but they're still linked together. It's amazing, and that's kind of what helps to describe the precisity of how we have the strong nuclear force, and then that does tie into gravity.
Right. Yeah. So it's not just that you get one of these values precisely where you need it to be. It's that these values are precise not only in their own current value, but they're also exactly precise in their relationship to all of the other values. Correct? Yeah. So it's not just enough that you change one of them. You would have to change all of them at the exact same time. And who knows what can happen with all of those things. If we look at the electromagnetic force versus the force of gravity, it is balanced to the same ratio as the force of gravity itself. 1 part in 10 to the 37th power. Okay? It has to be exactly that amount weaker than gravity, or it doesn't work. None of these things form complex molecules. None of these things form the heavier atoms that we need for life. And it all falls apart pretty quickly. Okay? And then weak nuclear force. So this governs how atoms radioactively decay. If you change the weak nuclear force and you slightly make it weaker, there's not enough helium to generate the heavy enough elements inside of stars, okay? So this means that things don't decay as quickly if you make it slightly weaker, okay? So that means whenever it forms an atom inside there, it doesn't want to decay. Like, sometimes you'll hear you'll talk about radioactive decay inside it, like you'll hear it in news articles, how uranium decays, how all of those things decay. If you change just a little bit weaker, they don't want to do that anymore, and you end up with more of the initial atoms that you want to. If you change it and you make it slightly stronger, all of the fuel in the stars burn out too quickly, and the supernova explosions don't scatter the heavy elements across the universe. Okay? Okay. We kind of talked about this. It's not just the ratio of, it's not just the number of these things to their own number, it's the ratio that all of these things happen. So if they estimate, if you change the strong nuclear force versus the electromagnetic force and make it slightly weaker, then anything that's higher than atomic number 5 becomes unstable. So if you change the nuclear force and make it slightly weaker, you don't get any carbon, you don't get any nitrogen, no oxygen, no magnesium, no sodium, all of these incredible elements that you have to permit life and photosynthesis and chemistry and all of those major things that you need to work. All right. Okay. So those are the initial conditions. Those are the glue, the physics glue that holds this world together. Okay? All of those things are balanced on a razor's edge. This is looking at the mass of the universe. Okay? So if you look at the mass of the universe, I wonder if that's on one of my second slides. We're going to cover it in a second. Okay, so the mass of the universe. Actually, let's do this. I'm going to go ahead for a smidgen. Okay. Can you all see this? Okay. The one on the left is the most zoomed in. The middle one is more zoomed out, and then the one on the right is what you would be looking at is if you were backed up as far as you could go. It's a measure of the cosmic background radiation, okay? It's basically as far backwards as you could look inside your microscope and still see something, okay? The really interesting thing when you look at the stars at night is that all of these things are pretty uniform when you're looking out at the stars. When you go out in your backyard, you don't see pieces of sky with just a lot of stars in it, and then pieces of sky with nothing in it. You know, assuming you could see past the glare of like the light from the city. If you go out into like one of those dark sky parks in the national parks and you can see the Milky Way across the entire galaxy, you do not see all of the stars in one place and then black sky in the other. What you see is you see a uniform distribution from one side of the universe to the other, where there's a relative amount of stars and a relative amount of black missing space inside the entire thing. You can really kind of see this in the center one. So look at that, and you can see how most of it is incredibly, like the stars are placed out there almost to precise increments. Okay? And if you back up all the way, each one of these little dots are little galaxies or galaxy clusters in there. So this uniform amount of matter and this uniform amount of stars exist not only just in little galaxies or little pockets of the universe, it exists everywhere you can look inside of the world. So each one of these, like I said, is a galaxy or a galaxy cluster. And if you notice, like there are pieces where there's a couple more stars, but on the whole, the entire thing is incredibly uniform, okay? How do we get that? If you look at this, this is an estimate of just the density of all of those things, okay? So we're looking at how much stuff is out there, okay? Just if we looked at all of the stuff outside of our telescope and we measured and weighed all of the galaxies out there, okay? The amount of stuff out there has to be precisely balanced against other stuff that's missing. Yes?
And to keep to keep in mind the relationship of everything that you're mentioning right now is we're talking about basically radiation. You know, you're talking about to get density, to get gravity, to get mass, all these things. You're talking about these how the nucleus of certain atoms reacts with one another. And radiation, in essence, are just isotopes. So it's basically the atom is unstable to the point of where it's trying to find another one that can compare with it, and it, boom, bonds with itself. That goes when it comes to electrons being emitted or taken in. So, and that's how you form these bonds, that's how you form density in X, Y, Z. So when you're talking about these forces, if you don't have an exchange, to keep in mind this bigger picture of what we're talking about, if you don't have it in this exchange at a rate that it needs to happen, then you can't have, so the force is right in the nucleus. You have protons and neutrons, right? And oftentimes, actually, they try to interchange with one another. So it's not just this one same proton, this one same neutron. They're actually interchanging really fast, okay, because of other things. But then because of this interaction, the electromagnetic field, for example, part of radiation, which, you know, light is radiation, but part of radiation is because of that interaction inside is causing the electrons on the outside to go crazy. They have so much energy, like, whoa, I'm going crazy, jumping from orbitals, jumping from this, that, and the other, gaining more energy, losing energy, and all of this, sometimes an electron pops off. And then that's how you get this isotope that's like, oh, I need to fill my electron back. And that's how you get this just interchange of energy between everything else. The galaxies, the stars, radiation outside the Earth, like you mentioned, I think 2 Sundays ago or last Sunday, when it comes to, you know, if the Earth was too close to the sun or not close enough or in orbital and everything like that, all this radiation would occur in amounts that it should not.
Yeah, right, exactly. So, so what happens if we take all the stuff out there that's in the universe, we measure it all up, we weigh all of the universes, all the galaxies that exist out there, and what happens if we have too much matter out there? What if we have too many galaxies out there, if there's too many stars? Does anyone know? We have too many, like if there was too much mass in the universe, if we added extra galaxies out there in the void pieces.
Did you have too much gravity? Gravitational pull between the objects?
It would collapse. That is exactly right. If you have too much mass inside of it, the gravity affects it, like you were saying, and then all of those pieces want to get themselves pulled back together. They have this reaction where they want to be close to one of each other due to gravity. And all of those things pull each other too close together, and the entire universe will collapse amongst itself.
You basically have an event horizon happening all over the place, and that's not a fun experience to experience. I mean, no one alive has experienced that, of course, but an event horizon would be the end.
Yeah, everybody dies at that point, yeah. So if you look at, and the amounts of stuff that's out there, this is called the mass density of the universe. If you weigh up all the galaxies out there, it is precisely balanced against gravity itself. So it's not just the case that gravity itself is precise, which it incredibly is. It's precise against all of the other the 3 fundamental forces of nature. And it's also precisely balanced with all the stuff that's in our universe right now. Okay? So they estimate that the total energy density is balancing each other to 1 part in 10 to the 20th power. Okay? What's 1 part in 10 to the 20th power? That's the number of seconds since time began. That's the number of seconds since time began. So those two numbers that's what we're talking about. All the numbers are the same except for the very last one after the decimal point. And if you mess with the amount of mass that's in the universe, just a tiny amount, everything dies. It either spreads apart too quickly, or it collapses amongst itself. Either way, you die. Okay, this is the expansion rate of the universe. This is the cosmological constant. A lot of physicists have trouble when they start looking at this. I've watched lots of interviews with physicists, and they all, whenever they look at this, they have this uncomfortable feeling, and they know that it's so precisely balanced that it makes them uncomfortable. One of the physicists that I was looking at says, all good physicists, put this number up on their wall and they worry about it because it's a problem, because it's so incredibly precisely balanced. So this balances the attractive force of gravity with the repulsive force of space, only observable at very large scales. So this is the expansion speed of the universe versus gravity. It is fine-tuned to 1 part in 10 to the 120th power. Okay? So 10 to the 36th power was the tape ruler that was all the way across the entire universe. Okay? Yes, Ms. Brown.
The reason why they're so uncomfortable is because that proves the existence of God.
Yeah.
Because
Here,
there's...
can you say that one more time?
Oh. I said the reason why the scientists are uncomfortable at that number is because it proves the existence of God.
Yes.
Because there is mathematically no way that this is random. So some of my favorite verses in the Bible are when God kind of got mad at Job, and he was talking to him, and this is in Job 37 and 38. It says, by the breath of God, ice is given. And then a little further down, it says, it's talking about the cloud and the moisture, and it says they turn around and around by his guidance to accomplish all that he commands them. And then if you go a little further down, it says, do you know the balancing of the clouds, the wondrous works of him who is perfect in knowledge? And a little further down, it says, can you, like him, what you were talking about, spread out the skies hard as a cast metal mirror?
Right.
So the ratios stay the same. And then in chapter 38, it says, where were you when I laid the foundation of the earth? Tell me if you have understanding.
Right.
So this is the foundation. You go a little further down, it says, where have you commanded the morning since your days began and caused the dawn to know its place, that it might take hold of the skirts of the earth and the wicked shaken out of it? And then further down it says, where is the way to the dwelling of light? And where is the place of darkness? So there's your black holes. And then the last verse is, can you bind the chains of the Pleiades, I'm probably mispronouncing that, or loose the cords of Orion? And so that's what all your numbers are saying.
Right. Right.
And that's in Job.
Yeah. No, that's an incredible thing where God is just, he's letting loose on him and saying, like, you have no comprehension of the things what you're talking about. Like, you can't come to me and say that life is unfair. Like, you are so far removed from everything that I've done for you. Like, you have no idea. That's exactly right. Yeah, so if you make the cosmological constant slightly more positive, the universe flies apart. And if you make it slightly negative, the universe collapses amongst itself. Yes, sir.
I think most folks have seen this, but the Hubble and the James Webb telescopes kind of destroyed the whole Big Bang theory. And it's pointing, for example, now they can look out to the theoretical edges of the universe. And the light coming from 14 billion years ago, they think it took that long to get to the Earth. Shows fully formed galaxies, fully formed stars, just like it was created spontaneously. There's no evolution. There's no forming of heavier elements from smaller elements inside of stars to create the matter that made the carbon and everything. It looks like spontaneous creation out as far back as they can see with the telescopes.
Right.
Instead of what they're talking about, the main sequence and evolution of the universe over
where the stars
infinite
explode and then they
time.
recombine themselves and stuff like that.
They recognize that there had to be a beginning because of the law of entropy, but they can't explain how a fully formed galaxy with fully formed stars could have existed 14 billion years ago. The galaxies closer to us and the galaxies that are the farthest remote, they look the same. I mean, the spectrum, as the astronomers look at it, the elements are there, the heavy elements are there 14 billion years ago.
They're already there,
Yeah,
right?
they're already there. So how else could it have happened unless there was a spontaneous creation?
Yeah, and to go along with that, if the universe is whatever it is, 96 billion miles apart, okay, which is what they've estimated, and it's 13 billion years old, but there's a uniform heat signature from one side of the universe to the other. So this is one of the problems that they're running into right now with the Big Bang Theory, and they've got a tweak to it, which they have no evidence for, but we'll give them their little tweak. So if you have a uniform heat signature, which is supposed to be the leftovers from the Big Bang, it's called the cosmic background radiation. So basically, if you measure the heat of space, it's 3 degrees above absolute zero everywhere you look, okay? And it's uniform from one side of the universe to the other. The only way that happens with thermodynamics is that the heat had to disperse itself evenly amongst all those pieces of the universe. So, in order for that to happen, the universe has to be in the same place at some point. It has to be close enough to itself to spread the heat from one side of the universe to the other. So if the universe is 13 billion years old and it's 90 billion years across, how do you get it to spread the heat energy from one side to the other? It's not old enough. It's bigger than it is old enough, okay? And so...
You got 2 minutes.
2 minutes.
The bells are not working.
Bells are not working. Okay, thank you, Lane. So if you look at this, how do you get the heat to spread itself from one side to the other? You can't do it with a Big Bang that just that starts at one point and it goes out evenly at that point. So what they do is they say, well, there was inflation, not monetary inflation like we're unfortunately living through right now. They say that it started at a single point, it rapidly expanded, and then it slowed down somehow, we don't know how. So it goes super fast for a microsecond, and then it goes really slow, but it expands at that point. So that's how you get something really far apart, but not really old comparatively. There's no evidence for any of that, but it is interesting that there is problems with the Big Bang Theory as stated right now, because then they're running into these. All right, I had some really cool stuff to show you guys, but we're out of time. I'll show you guys next week. Thank you all for all your comments. Appreciate it.